This is the story of a gap in optimization. Gradient descent was known to reduce the error at a 1 over k rate. A fundamental lower bound pointed to 1 over k squared, but no algorithm was known to achieve that faster rate. The story begins in 1847 with Cauchy's gradient method. At the current point, the gradient tells us the direction of greatest increase, so the method moves in the opposite direction. The update is simple. Subtract a step size times the gradient. This makes gradient descent inexpensive and widely useful, especially when a problem has many variables. For a smooth convex function, gradient descent guarantees the rate shown here, order 1 over k. This gives the starting point for the historical question. Could any first-order method be faster? To compare all first-order algorithms fairly, researchers used an oracle model. An algorithm chooses a point. The oracle returns the function value and the gradient at that point. Then the algorithm chooses again. This model focuses on information, not on one particular update formula. Every method receives the same kind of local data, so a lower bound in this model applies to every first-order strategy covered by it. In their 1983 work on optimization complexity, Arkady Nemirovsky and David Yudin asked a new kind of question. Instead of proposing another method, they searched for a speed limit that every first-order method must respect. They proved the result by considering carefully designed high-dimensional problems. The important idea is simple. Each oracle query reveals only limited new information, while part of the problem remains unresolved. By arranging where information becomes available, they showed that after k queries, an algorithm may still be unable to identify every direction needed for a more accurate solution. The conclusion was a 1 over k squared lower bound. In sufficiently high dimension, no first-order method in the model can guarantee an asymptotically better rate for smooth convex optimization. Every factor is now explicit. L is the smoothness constant. The norm is the distance from the starting point x0 to an optimizer x star, and that distance is squared. This point is essential. A lower bound is not an algorithm. It ruled out anything asymptotically faster than 1 over k squared, but it did not show that this rate could actually be reached. The situation was now organized clearly. Gradient descent guaranteed 1 over k. Complexity theory allowed, but did not provide 1 over k squared. The missing object was a method with a faster guarantee. At almost the same historical moment, Yuri Nesterov found the missing method. His paper was received in July 1982 and published in 1983. The title announced a convergence rate of 1 over k squared. The paper was only 5 pages long, but its conclusion was decisive. It gave a concrete first-order algorithm with the same rate that complexity theory had identified as the limit. In a common modern form, Nesterov's method first creates a look-ahead point. It combines the current iterate with the most recent displacement. The coefficient beta, k, controls how far it looks ahead. The gradient is evaluated at that look-ahead point, not at the current point. This use of previous motion together with a new gradient correction is the central idea behind Nesterov's accelerated gradient, or an AG. Most importantly, Nesterov proved a global 1 over k squared guarantee. The method did not merely look faster on examples. It achieved the rate required to close the theoretical gap. Now the two sides had the same dependence on k. The lower bound says that no method in the model can improve the order. Nesterov's upper bound shows that accelerated gradient attains that order. The conclusion is specific and strong. For smooth convex objectives in sufficiently high dimension and under the classical first-order oracle model, the 1 over k squared rate is asymptotically optimal. Acceleration later influenced composite optimization, restart methods, machine learning optimizers, and continuous time analysis. The formulas changed, but the central goal remained the same. Use first-order information as efficiently as possible. This is what makes the development so important. Nemirovsky and Yudin proved a fundamental limitation. Nesterov supplied a method that met it. A question about what was possible received a complete mathematical answer.